Thanks for joining me today. We're going to talk about exponents, and I'm going to do this by going through a series of example problems and just talking our way through it, and in the process we're going to develop a whole bunch of exponent rules. I'll write those down here on the side. The first rule that we come to is, of course, what is an exponent? And here's one way of representing it. So if I have a number, let's call it b, raised to a power, that is equal to b times b times b, as many as we need. How many? N times. So n, the exponent, is the number of times that we use b, the base, as a factor. So for our first problem here, we have 3 squared, a very simple one. That means take 3 and multiply it by itself, so that there's 2 3's multiplied together, 3 times 3, which is 9. Now, and when you're studying these and you're studying exponents and you're focused, you're not likely to make a mistake here, but I can tell you from experience that oftentimes when we're in the midst of the battle and we're doing a whole bunch of other operations, it's very tempting to say 3 squared is 3 times 2, which is 6. Everybody makes that mistake. So keep that in mind. When you see an exponent, just pause a moment, consider, think about it, and make sure that you're doing the base times the base, not times the exponent. Don't multiply it by the exponent. Okay, here's another tricky little problem. I put these together, negative 3 to the 4th power and negative 3 to the 4th power. What's the answer? Well, of course, 3 to the 4th power means 3 times 3 times 3 times 3. A really handy thing to do. I'm going to just write that down. 3 times 3 times 3 times 3. Really handy when dealing with exponents if you don't have a calculator handy, to kind of do them in pairs. So 3 times 3 is 9, and 3 times 3 is 9, and then 9 times 9 is 81. So the answer here is 81, and the answer here is 81. But what do we do about that parenthesis? Does it have any effect? And the answer is yes, it does. And here it is, and I'll try to explain this so that it makes some sense. Maybe it does, maybe it doesn't. In the end, you just have to follow the rules. The PEMDAS, remember the order of operations, PEMDAS says do the exponent, 4th power, before you do addition and subtraction, and so or multiplication and division. So you can think of that negative as negative 1 times 3. You can think of it as minus 3. However you think about it, that represents something that's going to be applied or done after the exponent. So we do the exponent first, 3 to the 4th power is 81, and then we apply the negative second. So that first one, negative 3 to the 4th power without parentheses, the answer is negative 81. But in the second case, negative 3 in parentheses to the 4th power, their order of operations says you do what's in the parentheses first. So that whole whatever we think about, that negative, it's been applied to the 3, and it's now one unit. It's one thing. And so this 4th power is being applied to that whole thing, to the negative as well. So let's think about that in our problem. Negative 3 times negative 3 is positive 9. Negative 3 times negative 3 is positive 9. And so we end up with a positive 81 instead of a negative 81. Okay, that's my best attempt at explaining how to deal with exponents of negative numbers, and remembering that the exponent gets applied before the negative unless the negative is in parentheses with the number on the exponents outside the parentheses. Okay, next one. Negative 17 in parentheses to the 0 power. What's the answer there? Well, this looks awkward and complicated until we remember one simple rule, and it's so simple and so nice that we oftentimes forget it. It goes like this. Any number raised to the power of 0 is equal to 1. Therefore, negative 17 to the 0 power is 1. That's it. Now, we'll come back to that one in just a minute. In fact, I'm going to slide my screen up a bit because we want to talk for a while about this next problem. And we'll see if that sheds any light on this weird rule. Let's talk about 2 to the 5th power over 2 to the 3rd power. I'm going to write that one out here. That's 2 times 2 times 2 times 2 times 2 over 2 times 2 times 2. Now, I could just do the math. 2 to the 5th power, 2, 4, 8, 16, 32 on top, divided by 2, 4, 8 on the bottom, and then I could figure out what that is, and 32 divided by 8 is 4. Okay, that's one way. There's another way that we can think about this with fractions. With common factors, we can just cross off common factors. So there's a pair of 2's that get canceled, another pair of 2's gets canceled, another pair of 2's gets canceled. Now, when we're doing this, we're actually dividing. So when we divide top and bottom by all those 2's, we're left with a 1 on the bottom. So 2 times 2 on top, 1 on the bottom, and that is 4 over 1, which is 4. So again, that worked. But there's another rule. And let's write this rule down. It's going to be really handy. The rule goes like this. B to the m power over b to the n power is equal to b to the m minus n power. Okay, put that in our notes, and let's apply it here. So here we have 2 to the 5th power over 2 to the 3rd power. The bases are the same, so we can say that's just 2 to the 5 minus 3 power. 5 minus 3 is 2, so 2 squared, which is 4, and once again we get the same answer. Now, you might be saying, well, then why did I even need that rule? Why don't I just do 32 divided by 8? Well, this is an easy or simple problem on purpose so that we can kind of see it mathematically, but if those 2's were variables or difficult bases, but difficult numbers to deal with, then this rule would be much easier and better to apply. Now, the rule can be extended. Let's take our example here and change it just a bit. What if it was 2 to the 3rd power over 2 to the 3rd power? You probably know what the answer is intuitively, but I'm going to write it out. 2 times 2 times 2 over 2 times 2 times 2. Of course, we could do it mathematically. That would be 8 over 8, which is 1. Or the 2's cancel, and another pair of 2's cancel, and another pair of 2's cancel, and we're left with nothing on top, nothing on the bottom, which is not 0. It's, remember, we're dividing, so it's just 1 over 1, which is 1. Or we could have said 2 to the 3rd power over 2 to the 3rd power, applying the rule, is 2 to the power of 3 minus 3. But wait, 3 minus 3 is 0, so this is 2 to the 0 power. And we have a rule that says 2 to the 0 power is equal to 1. So there's the proof for our b to the 0 power equals 1. Now, let me do one more. What if it was turned around? What if it was 2 to the 3rd power over 2 to the 5th power? Well, then we would have 2 times 2 times 2 on top, 2 times 2 times 2 times 2 times 2 on the bottom. We could write that as 8 over 32, or we can cross off pairs of 2's, and we're left with a 1 on top, and 2 times 2 on the bottom, which, either way you slice it, is 1/4. But what about our rule? Let's apply the rule. 2 to the third power minus 5. 2 to the 3 minus 5 power, which is 2 to the negative 2 power. And here we have another rule coming. The negative 2 power, or the negative power we just showed, means that the base and the exponent are going to end up in the denominator. So whenever we have a negative exponent, it means take that base and exponent, whatever it is, and move it to the denominator, or if it's in the denominator, move it to the numerator, move it to the opposite position. Okay, so that's really handy. Let's move on. And I'm going to see if I can get my eraser here to erase some of this stuff. Because we're going to move on to the next example. Now here in this example we have some stuff, 3 times x times y squared, in parentheses being raised to a power. And what it is we have a bunch of things being raised to a bunch of things being multiplied together and then raised to a power. And of course we can't multiply these particular things, 3 times x times y squared, we can't do that multiplication, but we can still apply the power. And here's the rule. It goes like this: a times b in parentheses to the power of n equals a to the n times b to the n. So we could call this the distributive property of powers. That's not really what it's called, but it kind of looks like the distributive property. And what happens is that power gets applied to each factor here. So that's 3 cubed, x cubed, and y squared cubed. Oh, wait a second. How do we do y squared cubed? We need another rule. If I have a number raised to a power, and then that whole thing raised to another power, we're going to multiply the powers. So b to the n times m power. Let's see how that works, and let's see if we can prove this a little bit. So y squared to the third power would mean y squared times y squared times y squared, which y squared is y times y, and then another y times y, and then another y times y, for a total of 1, 2, 3, 4, 5, 6 y's. So y, 6 y's being multiplied together is y to the 6th power, which is 2 times 3. So that's what we have, y to the 6th power. We have that x cubed, and then that 3 to the 3rd power, 3 times 3 times 3 is 27. And there we have our answer to this problem. Now, I forgot to put in another rule, and let's just throw it in here now. It's kind of implied, but y squared times y squared times y squared is really y to the 2 plus 2 plus 2 power. And here's the rule. b to the m power times b to the n power is b to the m plus n power. Now, I did this kind of out of order, but pay close attention to the difference between these two problems. One is you're multiplying two bases that are the same with exponents. You add the exponents. One is you're taking one single base with an exponent and raising that whole thing to a power. You multiply the powers together. Okay, let's do a couple of hard questions that try to put all this together. I don't think I have any more rules. Maybe I'll use a different color for this one. So for this problem, I have, my parentheses aren't very good, but they're covering the whole fraction here. So I have negative 2mn to the negative 2 power over 5, and that's to the power of 3. And there's really not a whole lot of simplifying I can do inside the parentheses. There's a little bit. I can take that n to the negative 2 power and move it to the denominator. So maybe I'll do that first. So this is negative 2m over 5n squared, right? Because the n to the negative 2 power, that negative 2 just means take that base n and the power 2 and move it, the whole thing in mass, to the other side. That's what the negative does, and then it's no longer negative. It's just saying I'm in the wrong spot. I'm in the numerator, I should be in the denominator. Okay, now we're going to apply the third power to this, and we're going to apply to each part, and I guess I do have another rule here. Here we go. How about a over b to the power of n equals a to the n over b to the n. So this is just the same as that first rule on the page at the top there. It's just saying that the powers can be distributed to the numerator and denominator, just like so the quotients, the parts of the quotient, just like they are to the factors in a product. Okay, so this is going to be, well, we need to put that negative somewhere, because it's going to be negative cubed. So a negative squared, a negative times a negative is positive. Negative cubed is negative times a negative, positive times another negative is negative. So the final answer is going to be negative. Then 2 cubed, well, let's write it out. 2 cubed, m cubed, 5 cubed, and then n squared cubed is 6 power. And so we can round this out as negative 2 cubed is 8, m cubed, 5 cubed, 5 times 5 is 25, times 5 is 125, n to the 6 power. Where did that 6 come from? Well, n squared, remember it was n to the negative 2 power in the numerator, I got moved to the denominator, raised to the third power, 2 times 3, applying this rule, is n to the 6th power. And there's our final answer. Okay, hit pause and try that last one. See how you can do putting all of this together. Well, there's a lot of stuff going on here. So I'm going to do that parenthesis, and there's nothing that can be done in the parenthesis other than move that y to the negative 2 power to the denominator, but I can't do that yet because the numerator, that bit in the numerator is in the parenthesis, but the denominator of the fraction is not in the same parenthesis. So that negative 5 is going to get applied to the y to the negative 2 power, but if I moved it down to the denominator, it would not, it would be out of reach of that little 5th power there. So I'm going to keep that. So I'm going to apply the 5th power to the y to the negative 2 and to the z. I'll do that first. So 25x, those are outside the parentheses, so they're not impacted by that 5th power. The 5th power is going to be applied to the y to the negative 2, so that's y negative 2 times 5 is negative 10. And then z to the 5th power as well. Now for the denominator, I'll do the same thing. I'm going to apply the 3rd power to everything in the parentheses. So 5 to the 3rd power, x to to the third power, y to the, well, let's say it's already the third power. 3 times 3 is 9. Z squared to the third power is z to the sixth power. And now I need to think of this as a series of fractions that can be simplified. We have 25 over 5 cubed. That's one fraction. We have x over x cubed. That's another. Y to the negative 10 over y to the ninth. That's a third. And then z to the fifth over z to the sixth. So all of those can be simplified. There's a couple of ways to think about 25 over 5 to the third. One way is to use exponents. So 25 is really 5 squared over 5 cubed, which is 5 to the 2 minus 3 power, which is 5 to the negative 1 power, which is 1 over 5. So that part of the answer is 1 over 5. Now, the whole answer is going to be one big fraction, so in that fraction there's going to be a 5 in the denominator. We'll do the same thing with the x's. We have x to the first power over x to the third power. That's x to the 1 minus 3, which is x to the negative 2 power, which is 1 over x squared. So that just means the x squared goes in the denominator also. Let's do the same thing with the y's. So we have y to the 10th, negative 10 power, and y over y to the 9th, so it's negative 10 minus 9. Well, look at that, that's y to the negative 19 power. Again, that means y to the 19th power goes in the denominator. And then z to the 5th over z to the 6th is z to the 5 minus 6, which is z to the negative 1. Again, z goes in the denominator. And what goes in the numerator? Well, there's nothing there, but remember that this is all multiplication and division. So when we're dividing out factors and doing stuff. So there's nothing left when we're doing these kinds of problems. We leave a 1 there. And it's kind of like reducing that fraction, that first fraction, 1/5. There was a 1 on top. So we can use that, we can borrow that 1 and use it for our numerator, since nothing else ended up being there. If there had been something else, it would have been 1 times whatever that was, but there was nothing there. So there is our final answer. Well, that's a crazy one. Thank you very much for watching.